In the beginning, I told you we will discuss two cases in the working of JFET, and in this lecture we will discuss the case number 2. We have already completed the case number 1. If you missed the case number 1, you will find the link in the description. In case number 1, VGS, gate to source voltage, was equal to 0 volt and VDS, drain to source voltage, was equal to VDD, where VDD is some positive voltage. In case number 2, VGS is negative, it is less than 0 volt, and VDS is, let's say, equal to VDD prime, and if you compare VDD and VDD prime, then you will find VDD prime is less than VDD. Now there is one specific reason for keeping VDS lower than the VDS in case number 1. I will explain the reason. The prime aim in case number 2 is to obtain the saturation, the saturation at lower value of drain to source voltage VDS. So we want to obtain the saturation at lower value of VDS, and because of this, VDS in case number 2 is smaller than VDS in case number 1. Now I will explain what do we mean by saturation. Saturation is a condition in which the drain current ID remains constant with change in drain to source voltage VDS. So when you change VDS and ID remains constant, we call this condition saturation condition. In the case number 1, when VGS is equal to 0 volt and when VDS is greater than magnitude of pinch voltage VP, then ID is equal to IDSS. IDSS is a constant current and it is the maximum drain current. So in case number 2, when ID becomes constant, we cannot say that ID is equal to IDSS, because for IDSS VGS must be equal to 0 volt. But in case number 2, VGS is negative, it is less than 0 volt, so ID is not equal to IDSS in case number 2. Now let us see how we can obtain the saturation condition in case number 2. You can see VDS is smaller compared to case number 1, and when VDS is smaller, we need to make VGS more negative. And we are doing this to have the same width of depletion region as in case number 1. So the things are now clear. In case number 1, we had larger VDS, and for that we made VGS equal to 0 volt. But in this case, VDS is smaller, and to get the same width of depletion region, we need to make VGS more negative. So I will connect the gate terminal to the negative polarity of the voltage source and the positive terminal to the source terminal, and then we will connect the source terminal to the negative terminal of the voltage source and the drain terminal to the positive terminal of the voltage source. This is the drain terminal, and because of this, the width of depletion region will now change, and current ID will flow. The gate current IG will remain 0 amp because of reverse biased PN junction. The source current is having the direction like this. IS is the source current. I will connect the source to the ground. So this is the circuit, and let's say VGS plus minus VGS is equal to -1 volt. So this battery here will have voltage equal to 1 volt. Because of the polarity, VGS is equal to -1 volt. Here the battery is equal to VDD prime, which is equal to VDS, and when this is the circuit, the width of depletion region will increase because P type is connected to the lower potential and N type is connected to the higher potential. The same thing is true for this P type material. P type is connected to this common terminal and the gate is at the lower potential, so P type is connected to the lower potential and N type is connected to the higher potential. So the two PN junctions are reverse biased and the width of depletion region will increase. Now on increasing VDS, width of depletion region will increase further. The width will increase more at the top as compared to the bottom, and after some time it will appear that the two depletion regions are touching each other, and this condition is known as pinch-off condition, and the corresponding VDS, corresponding drain to source voltage, is called as pinch-off voltage. And if we compare the pinch-off voltage in case number 1 with the pinch-off voltage in case number 2, then pinch-off voltage in case number 1 is more as compared to the pinch-off voltage in case number 2. We are getting lower pinch-off voltage in case number 2 because gate is negatively biased. Now what will happen to the drain current ID if we increase VDS beyond the pinch-off voltage? We have already discussed this point. If we increase VDS beyond pinch-off voltage, ID will remain constant. This is called as saturation condition. So we have achieved the thing we were looking for. We have the saturation condition, ID is constant, and the main thing is that VDS is relatively smaller as compared to the case number 1. We are getting saturation condition for lower value of VDS as compared to case number 1. Now I will quickly draw the pinch-off condition, and you can see that the two depletion regions appear to touch each other, and when this happens, the current ID will become constant. If you increase VDS more, ID will remain same, and this condition is called as saturation condition. So we can say that by applying negative bias to the gate, the saturation level can be reached at the lower level of VDS. So this is all for this lecture. In the next lecture we will discuss VI characteristics of junction field effect transistor. The next lecture is very important. We will plot ID versus VDS plot for various gate to source voltages.